Good evening, everybody. Good evening, and thank you so much for being here. My name is Jen Scanlon, and I'm the Dean for Academic Affairs, and I'm standing in tonight for President Clayton Rose, who at the last minute was unable to be here, so I'll do my best. I know that what he would say by way of starting is that these endowed professorship talks are really among the most important things that we do at the college to recognize people's excellence. And I'm just so happy that you're all here tonight as we will celebrate Professor Jennifer Taback and her accomplishments and her being named to the Isaac Henry Wing Professorship of Mathematics. I also should say that welcome also to all of the people who are with us through live stream. So I guess that's one of the benefits of the pandemic is we mastered some technological things, one of which is to allow a far greater number of people than the wonderful group that's here to be present for Jen's talk. So again, welcome to the Isaac Henry Wing Professorship of Mathematics lecture. The Wing Professorship is over a century old, having been established in 1906 by Isaac Henry Wing, Bowdoin class of 1856. Wing was a kind of jack of all trades who served as a frontier lawyer, some of these things I'm not sure what they are, but a frontier lawyer, an accountant, a judge, a police judge, a land surveyor, and a Civil War Union Army veteran. He enjoyed math, loved math, and created this professorship mainly for that reason, just simply because he loved mathematics. Our speaker and honoree is Professor Jennifer Taback, who is the 8th holder of this professorship and the first woman to hold this chair. She joins a group of extraordinary Bowdoin mathematicians who have been named Wing professors, including most recently Professor Bill Barker, and stretching all the way back to William Albion Moody in 1907. So let me tell you a little bit about Professor Taback. Professor Taback arrived at Bowdoin in 2004, this says, but that's wrong because she and I both came here in 2002, and we know it. We know that we did. From the University of Albany, having previously taught at the University of California, Berkeley, and the University of Chicago. And she was celebrated at both Berkeley and Chicago with teaching awards. These awards hinted at the kind of extraordinary faculty member Jen would become at Bowdoin College, a dedicated and inspiring teacher, an insightful, influential, and collaborative scholar, and a fervent and impactful advocate for math education among underrepresented groups and in our local Mid-Coast community. And I know that many of her present and former Brunswick High School mathematics students are here tonight. Jen's research and scholarship focuses on metric and combinatorial properties of something called infinite finitely generated groups, which sounds like an oxymoron, but maybe we will figure out what that means. She's published papers on topics with some pretty remarkable titles like Quasi-Isometric Rigidity, Twisted Conjugacy Classes, and Lamplighter and Distal Leader Groups. Jen is deeply committed to collaborative work, and she's received a Simons Foundation grant, 2 Mellon Foundation grants, and 4 National Science Foundation grants to advance and share her scholarship. Jen is well known among her academic peers in the math community, not only for her research and collaboration, but also for her service to the Academy. For more than a decade, for example, she served in various leadership roles within the American Mathematical Society, including as a member of the Council and the Executive Committee, and in her current role as co-chair of the Next Generation Fundraising Committee. On campus, Jen is known better as a passionate and caring teacher who makes incredibly difficult concepts understandable. She is an extraordinary mentor for students, and in particular is devoted to encouraging young women to continue and deepen their interest in math. To this end, she currently serves as the faculty advisor to the Bowdoin student chapter of the Association for Women in Mathematics. Jen is basically a math zealot, and she uses her infectious enthusiasm for the subject to excite members of our surrounding community as well, as I mentioned. As part of her ongoing campaign to build and to sustain a mathematical community in Mid-Coast Maine, she co-founded and co-leads the Bowdoin College Math Circle, which engages local junior high school students in discussion about math topics. She's also brought together math faculty at Bowdoin, Bates, and Colby through a recurring joint seminar, which has hosted speakers from colleges and universities around the country. Jen received her undergraduate degree in mathematics from Yale University and her master's and PhD from the University of Chicago. Her love and passion for mathematics is evident, as we will all see in a minute. That love and passion sweeps along students. It also sweeps along her colleagues and the community that surrounds the college. I can't imagine a more worthy recipient of tonight's honor. For all of these reasons, I am delighted to introduce Jen Taback tonight as our Isaac Henry Wing Professor of Mathematics.
Thank you. First, I would like to thank Dean Scanlon for her kind and generous remarks. I am touched and honored to see so many people from different parts of my life in the audience today, and know that many more of you, including family members, friends from elementary school and beyond, and former students, are joining us tonight via live stream. It is a great honor to join the list of distinguished faculty who have held the Wing Professorship and who have devoted their careers to serving the profession of mathematics and the students of Bowdoin College. So when people learn that I am a mathematician, they often ask me a variety of questions. The most common one is a version of the following. So what is it exactly that you do? Isn't all of math already known? Isn't it all written down in a book? And when they think of books, they mean sort of dusty old books. So in my time with you today, I want to address the following question. How does mathematics change over time? Who changes mathematics and pushes it in new directions with new applications? So I will use the history of geometry to show that mathematics is a dynamic discipline, changing like any other scholarly field when bold people question its assumptions and their implications. Geometry is also a branch of mathematics which we can all relate to. Triangles, polygons, area, perimeter, though many of us may associate it with those two-column proofs from high school geometry. It's a topic that many assume was codified by Euclid in the Elements and hasn't changed since. However, the story I will tell you today will illuminate the twists and turns, sometimes radical, which geometry has taken over many centuries, leading to surprisingly modern applications. Geometry is also an area of math which I rely on in my research, though in ways different than high school geometry might suggest. So I work in an area of math called geometric group theory. So group theory, before we get to the geometry part, group theory is a branch of mathematics which studies symmetries of objects. So here I've depicted a pyramid and its symmetries, which you can imagine as rotating it along various axes. The problem is that when we go down to write these down, we get something like this, which is actually just a page from the group theory textbook I'm teaching from. My students might recognize this. And then it kind of loses its meaning. I mean, what does a to the 10th power mean? What is a? Okay. So to visually understand a set of symmetries, we borrow from a mathematical area called combinatorics. And we represent our symmetries as a graph. So each symmetry, each one of these possible rotations of my pyramid is going to correspond to a point in my graph, and we use edges to denote the relationships or the special relationships between the different symmetries. So now we've turned something that looks like this, that nobody really wants to decipher, into something that has a nice picture that we can try to understand. So we also, when we think about our symmetries as a graph, we now have a way of measuring something like a distance between symmetries. I can take this dot, which represents one symmetry, and this dot, which represents another, and I can say, well, these are 3 apart because there are 3 edges between them. So once we have a way of measuring distance by counting edges, we can borrow tools and questions from other areas of mathematics called geometry and topology. So geometry is simply the study of properties of objects that can be measured. Area, perimeter, angles, that's geometry. Topology is the study of properties of objects which do not change when you twist or stretch the object as if it was made out of rubber. So for example, a donut made out of rubber, I don't know why you'd want that, but if I stretch it, it always has a hole in it. So the goal of geometric group theory is to use ideas and tools from geometry and topology to draw algebraic conclusions about our set of symmetries. So geometry is something that I rely on constantly in my research. I want to begin the story of geometry with the Pythagorean theorem, which many of us may remember from high school geometry. So the Pythagorean theorem relates the 3 sides of a right triangle, if I call them A, B, and C, in the algebraic relationship a squared plus b squared equals c squared. We view this as a great achievement of Pythagoras and the ancient Greek geometers. However, the Pythagorean theorem does not belong to the Hellenic geometers. This relationship between the sides of a right triangle has much broader beginnings. Over 1,000 years before Pythagoras, there is evidence of Pythagorean triples, that is, 3 whole numbers that satisfy the relationship a squared plus b squared equals c squared, on Babylonian tablets, though written in base 60, which formed the basis of their number system. A few hundred years prior to Pythagoras, Indian mathematicians wrote manuscripts with evidence that they also understood this theorem, as did ancient Chinese mathematicians more contemporary with Pythagoras. Paulus Gerdes, in his book, Geometry from Africa, makes a strong argument that the diagrams for a proof of this theorem can be found in Kenyan basket weaving patterns. So even something we thought so clearly attributed to Pythagoras and the Greek school of geometry demonstrates that geometric ideas were studied by many ancient civilizations, way more than the 4 mentioned here and documented in their manuscripts. So the history of geometry begins much more broadly than we usually view it. So what did Euclid do for geometry, right? He's often called the father of geometry. What did he do if it started so much earlier? Well, he did 2 things. First, he wrote it down. Right? He codified the current geometric knowledge of his time, much of it influenced by interactions with other cultures of his day, in the 13 books of the Elements. And this is a particularly beautifully engraved copy of the Elements. So Euclid's second contribution shaped mathematics in a more fundamental way. He provided a context in which to study and understand mathematics by stipulating a short list of postulates or assumptions and decreeing that all other statements should follow from them with a logical argument referencing your assumptions. He set the stage for modern mathematical rigor and argument. This is still how we develop and justify mathematical theory today. So what are these postulates or assumptions that Euclid made? So here they are. The first 4 are short, simple, intuitive statements. 2 points determine a line. A line segment can be extended indefinitely in both directions. The 5th, or parallel postulate, is more complicated and was even more complicated in Euclid's original phrasing. So it says, given a line, L, the blue line, and a point P not on the line, there is exactly one line that you can draw through P which does not intersect L. And I did that. I drew the green line, which is the line parallel to the blue line. And if I tilted it even a tiny bit, I would get something like the orange line, which would eventually intersect my blue line. So we know from experience that there's only one line through P that's parallel to L. So even in Euclid's time, mathematicians, using that term in the broadest sense, were troubled by the complexity of the parallel postulate. It is not short and simple. It requires at least one diagram. So the natural reaction was to attempt to prove that you didn't need it, that the parallel postulate followed from the other 4 assumptions, and thus did not need to be on that list. This problem puzzled mathematicians for over a millennium. Did the parallel postulate actually follow from the other 4? I know that my students are troubled by a problem which takes them a week to solve, and this is on an entirely different scale. So the history of geometry is not at all straightforward. For over 1,000 years, people questioned its assumptions and tried to see whether or not they could be simplified. Eventually, a variety of scholars in different countries and in different centuries began to entertain the notion that there might be a different kind of geometry if the parallel postulate failed or was removed from this starting list of assumptions. What would this do to geometry, which we call Euclidean geometry? So there are 2 basic ways that the parallel postulate might fail. We might have a type of geometry in which there are no parallel lines, in which every pair of lines intersects. Now, you're thinking, this doesn't happen. This is not how it works. So I give you that. This does not happen in high school geometry. Okay? So in Euclidean geometry, we have a parallel line. But maybe there's a type of geometry where there are no parallel lines. Or we might have a type of geometry in which there are infinitely many lines through our point P which don't intersect our starting line. Again, not something which has ever occurred in our understanding of geometry. Sorry, lost my iPad seems to have a mind of its own. Okay. So each of these possibilities gives rise to a completely different geometric system. Allowing exactly one parallel line leads to Euclidean geometry, where we have a lot of geometric intuition. Allowing no parallel lines, so a geometry where all lines necessarily intersect, leads to spherical geometry, the geometry of the Earth and of navigation and cartography. Allowing infinitely many parallel lines introduces a new theory of non-Euclidean geometry. So the history of geometry is not a straight road from ancient Athens to your high school geometry classroom. We are about to see that it branches into 3 radically divergent pathways. So let's begin our broader understanding of geometry with spherical geometry, the geometry of the Earth. So just as standard high school geometry is drawn in the Euclidean plane, which we envision as a sheet of paper, spherical geometry is drawn on the surface of a sphere. So what are the lines in spherical geometry? A line, also called a geodesic, in any type of geometry represents the shortest distance between 2 points. In spherical geometry, a line will represent the shortest distance between 2 points on a sphere. In spherical geometry, our lines will be great circles. That is the largest circle you can draw on the surface of a sphere. So the equator is a great circle, as is any line of longitude. So why are there no parallel lines in spherical geometry? So don't look at the triangles yet, just look at the lines. So take the equator, which I'll think of as this yellow line over here, and look at point C, which we can imagine to be the North Pole. So any great circle, any line of longitude through the North Pole necessarily has to intersect the equator. Okay? And we could adapt this picture by rotating our sphere and conclude that any 2 great circles or spherical lines must intersect. So this is a geometry where every 2 lines intersect. We can use 3 great circles to form a spherical triangle depicted in either image on the screen. I want to point out something very strange in the triangle on the right, this red triangle over here. So if I imagine these spherical lines as lines of longitude, I can kind of adjust them until I have a 90-degree angle up at the top over here. But then I also have a 90-degree angle over here, and I have a 90-degree angle over there. And now I have a triangle with 3 right angles whose angle sum is 270 degrees. And this viscerally contradicts our notion that the sum of the angles in a triangle is 180 degrees. So spherical triangles have very different properties from our regular triangles. So if great circles are the lines on a sphere, and a line is always the shortest distance between 2 points, It follows that ancient and modern civilizations should use this geometry for navigation, whether by boat or by plane. And this is indeed how airplane routes are determined. If you have taken a long flight and followed the path of your airplane, you have probably seen something like this on the little monitor on the back of your seat. So why doesn't this airplane fly in a straight line from Tokyo to Los Angeles? It's because airplanes, which want to go in the shortest path from Tokyo to Los Angeles, follow great circle routes, which are round because they're spherical lines. Okay? And you can find all sorts of fun calculators online which tell you the difference in nautical miles between the Great Circle Route, here between Florida and Portugal, and what looks to us like a straight line. And if you look at the numbers up here, you'll see that the Great Circle Route is roughly 200 nautical miles shorter. So a visual way to highlight the differences between Euclidean geometry and spherical geometry is to imagine a globe and a map. Imagine an orange on which the countries of the world are drawn as your globe. This exhibits the geometry of the sphere. To create a map for your atlas, we must peel that orange and press the peel flat on a piece of paper. Right? That is, we must flatten spherical geometry into Euclidean geometry. Now, this causes a lot of distortion in your maps. In the standard Mercator projection used for most maps, Greenland and South America appear to have the same area, which is certainly not the case on a globe. This is exactly because spherical geometry and Euclidean geometry have very different properties, and spherical geometry belongs on a sphere, not on a flat piece of paper. Now, if you're very careful, you can try peeling that orange in a way that you can press flat on a piece of paper, in a way that doesn't distort area. And here are two examples of how you might do that. I don't think I could actually do either one of these, but here are two examples. And I suspect we would be very confused if we tried to read these maps, if we found them in an atlas. But I will tell you that they have a lot less distortion than the standard maps that we use today. So now that we've talked a little bit about spherical geometry, let's return to the third kind of geometry, the really unknown kind of geometry, the one in which we allow the parallel postulate to fail spectacularly and allow an infinite collection of lines parallel to a starting line. So this will be called hyperbolic geometry. So in the history of geometry, we have moved up to the late 18th and early 19th centuries, more than 2 millennia from Euclid's codification of geometry into the elements. And still, no one has been able to resolve the question of whether the parallel postulate follows from the other 4 postulates. D'Alembert, writing in 1767, referred to the state of this problem as the scandal of elementary geometry. And Gauss, the most preeminent mathematician of his day, wrote in 1813, "In the theory of parallels, we are now not farther than Euclid. This is a shameful part of mathematics." I have a very abridged list here of some of the scholars from many cultures and over many centuries who tried to prove that the parallel postulate was either dependent on or independent of the earlier postulates. You might recognize some names on this list, and it is only a small sample of the mathematicians who engaged mightily with this problem. Our story changes abruptly in the first half of the 19th century, as 3 mathematicians at different stages of their careers each independently made strides to recognizing a new geometry satisfying the first 4 postulates of Euclid, but a very different theory of parallel or non-intersecting lines. The most thorough and complete approach was taken by Carl Friedrich Gauss, over here on the left, the most well-known and influential mathematician of his day, whose work has shaped many fields of modern mathematics. Gauss developed a consistent theory for this new geometry, but at the height of his career, secure in his mathematical renown, he decided not to publish his work. One story claims that the philosopher Immanuel Kant had stated that Euclidean geometry was, quote, "the inevitable necessity of thought, leaving no room for any non-Euclidean theory of geometry," and Gauss just did not want to get into it with Kant on that issue. So Gauss discussed this new theory of geometry with a friend and mathematician, Farkas Bolyai, who himself had tried to prove the dependence of the parallel postulate on the 4 earlier postulates. He was on my list on the previous slide. And Bolyai warned his son, János, also a mathematician, away from this topic, writing to him, "You must not attempt this approach to parallels. I know this way to the very end. I have traversed this bottomless night, which extinguished all light and joy in my life." They were a little dramatic. "I entreat you, leave the science of parallels alone. Learn from my example." Did he? As with many children who don't always listen to everything their parents recommend, the younger Bolyai could not resist the lure of such a fascinating problem so long unsolved, and eventually actually succeeded in developing the foundations of a new theory of non-Euclidean geometry. Upon seeing this work, Gauss, acknowledging Bolyai Gauss declared Bolyai a genius of the first order, but refused to acknowledge this work publicly, writing to the father, Farkas Bolyai, to praise it, meaning Bolyai's work, would amount to praising myself, for the entire content of the work coincides almost exactly with my own meditations, which have occupied my mind for the past 30 or 35 years. Although he worked on many mathematical problems for the remainder of his career, János Bolyai never published another manuscript. Contemporaneously in Russia, mathematician Nikolai Lobachevsky was developing an analogous theory of non-Euclidean geometry. Neither Gauss nor Bolyai knew of Lobachevsky's work, as the internet was often down in the 19th century, and it was hard for information to spread between mathematicians working thousands of miles apart. However, in 1837, Lobachevsky's work was finally published in Europe, but it was neither widely nor well received. Lobachevsky in particular was interested in the trigonometry of his new geometry, which reflected his research interests in both physics and astronomy. While he never felt sufficiently recognized for his mathematical contributions, he led his university, the University of Kazan, as an admired administrator for many years. So in order to describe this new type of geometry, called hyperbolic geometry, I have to take you from the theoretical statement, Gauss, Bolyai, and Lobachevsky proved mathematically that this alternate geometry exists, to the practical, what does this geometry look like? And to do this, we have to answer 2 questions. First, where do we draw this geometry, this hyperbolic geometry? Euclidean geometry is drawn in the Euclidean plane, which we envision as a flat sheet of paper. Spherical geometry is drawn on the surface of a sphere, which we envision as the Earth. While many mathematicians have created different models for hyperbolic geometry, I'll describe one due to mathematician Henri Poincaré, called the Poincaré model of the hyperbolic plane. Perhaps surprisingly, this model of hyperbolic geometry is drawn inside a circle, and we call the circle the boundary circle of the hyperbolic plane. The second question I have to answer is, what are the lines in this geometry? A line will represent the shortest path between 2 points in the hyperbolic plane. In hyperbolic geometry, the lines are going to be pieces of circles perpendicular to the black circle. So in my image over here, each of these blue lines is an actual hyperbolic line in the hyperbolic plane. So this is very different. You're going to have to just kind of go with me for a little bit. This is very different. Okay? So why does this geometry, with this idea of a line, allow infinitely many parallels, which is how I advertised it? So believing in truth in advertising, let's think about parallel lines. So here I have a hyperbolic line over here, and I chose a point not on the line. And so I'm really asking the question, how do I draw a line through P which doesn't intersect my blue line? And here I've drawn quite a few. All of these green pieces of circles are hyperbolic lines. So there are 4 of them over here, and by shifting them just a little bit, I could draw infinitely many hyperbolic lines through this point that don't intersect L. So if you're willing to believe me that I can invent a new geometry that happens inside this circle with these being my lines, then it does satisfy that there are infinitely many parallel lines. Okay, kind of out there. So what does this geometry look like? Well, a good place to start understanding a geometry is to say, what does a triangle look like? Because we all like triangles. So in any geometry, a triangle is formed by taking three lines which intersect in a particular way. To form a hyperbolic triangle, I take three hyperbolic lines, and I let them intersect. And each of these yellow regions is a hyperbolic triangle. We see three hyperbolic triangles over here. Okay. As these triangles are formed from hyperbolic lines, their sides appear curved to us with our Euclidean glasses on. And we notice another oddity. As the vertices of the triangle get closer to that boundary of the hyperbolic plane, the angles look small and very pinched. Okay, you can see that over here. These angles look small and really pinched. Okay, in fact, as the vertices of my triangle move closer and closer to the edge of the hyperbolic plane, I can make these angles as close to 0 degrees as I want. So hyperbolic triangles are very different from the flat triangles of Euclidean space and the round triangles of spherical geometry. So moving beyond the pretty triangles, you might start to question the size of the hyperbolic plane. After all, my circle is quite small. How interesting and complex can a geometry be if it all happens inside this tiny little circle? So this is really a question about how we measure length in the hyperbolic plane. Your standard Euclidean ruler does not work anymore. Instead, to measure hyperbolic length, we first measure with our Euclidean ruler, and then we divide that number by how close we are to the edge of the hyperbolic plane. So this sounds complicated, so let's see what it means. So I drew some little tiny red segments over here, and I meant them to be the same size to us. As we look at them, we would probably agree all those red segments are the same size. So they are the same size in Euclidean length. To get their hyperbolic length, I have to divide by the distance to the edge of my circle. So let's just assume my circle has radius 1. So I drew the first one kind of in the middle of the circle. So if I call its Euclidean length L, its hyperbolic length is L divided by 1, which is L. But this one over here, its distance to the edge of the circle is a half. So its hyperbolic length is L divided by 1/2. This is the hardest math you'll have to do in this talk. L divided by 1/2 is 2L. So in the hyperbolic sense, this little red segment is twice the length of that one. And similarly, this one over here, its distance 1/4 from the edge of the hyperbolic plane. So its hyperbolic length is L divided by 1/4, which is 4L. And then if I draw one all the way over here, maybe its distance to the edge here is 1/10,000. So its hyperbolic length is 10,000 L. So if I look at this little red segment and that little red segment, the one over here is 10,000 times the length of the first one. So this is very strange. Right? If I stood up here with an actual ruler and I measured 12 inches at the front of the auditorium and 12 inches at the back, it would be the same 12 inches. That's not how it works in the hyperbolic plane. It matters where you are. Your ruler changes depending on where you are. Here's another way to think about the hyperbolic way of measuring things. If I wanted right over here to draw a segment that still had hyperbolic length L, like this one does, I would have to make it half as long. Because right over here, to get the hyperbolic length, I multiply it by 2. And if I wanted a segment over here that also had hyperbolic length L, I would have to make it 1/4 as long, because over there, I multiply by 4. So this is just a very different way of measuring things than we have in the Euclidean plane, where your ruler is the same no matter where you're standing, right? If we were standing in the hyperbolic plane, I would need a different ruler up here than all the way at the back of the auditorium. It's very strange. Okay? But this doesn't quite answer the question of whether the hyperbolic plane is infinite. Right? It just tells us that there's a weird measuring system. So let's apply this same reasoning to a radius of my circle. Again, I have marked off small segments over here, which should look to be about the same length with our Euclidean ruler. But if we scale these segments By how close they are to the edge of the circle, we'll get their hyperbolic length. So if I take a segment over here, which maybe has length L, and a segment over here, which is really, really, really close to the edge of the circle, then that segment might have, say, length 10 million times L. So by shifting my segments that look the same to us closer and closer and closer to the edge of the circle, actually, they get longer and longer and longer and longer. This is very strange. And it turns out that in the hyperbolic way of measuring things, this radius, which over here in the Euclidean sense has radius 1, is infinite in its hyperbolic length. It's very strange. So even though it looks to us like the hyperbolic plane is a small circle, it actually, in the hyperbolic way of measuring things, it contains an infinitude of space. That's already enough to make your head hurt just a little bit. Here's another way to think about it. Suppose a person goes out for a walk in the hyperbolic plane. Now, that person does not change size along the walk. But as the person moves closer to the boundary of the hyperbolic plane, their hyperbolic size remains the same, but their Euclidean size gets smaller because I would be multiplying it by larger and larger and larger numbers as they get closer to the edge. So if we were watching a person going for a walk in the hyperbolic plane, they would look smaller and smaller to us as they walk towards the edge of the boundary circle. It's very strange, this hyperbolic geometry. Now I'm about to claim that you've seen it before. And I know some of you are thinking, not me, that person. Okay, so, all right. How have you seen this before? Well, many of you have seen some of Escher's circular engravings, part of his circle limit series. So in the middle image, called circle limit 4, sometimes also called angels and devils, we see the white angels and the black devils. Now the angels seem smaller and smaller to us as they are drawn closer to the edge of the circle. Now Escher was a self-taught mathematician, and he understood the principles of a hyperbolic ruler. When he created the circle limit series, he intended for all of the angels to have the same hyperbolic size, which necessitated that they were drawn smaller in the Euclidean sense as they got closer to the boundary of the hyperbolic plane. Escher understood that infinitely many equally sized angels or devils would fit into the hyperbolic plane because the hyperbolic plane had its own rules of measurement and contained an infinitude of space. And if we look at circle limit 3, which is the one over here, which contains fish, we again see that the fish look smaller to us as they get closer to the boundary circle of the hyperbolic plane. And again, Escher understood that this image exists in the hyperbolic plane, in which case all the fish are identical in their hyperbolic size. Now, if we look at the white spines along the back of the fish, here or there, we see that they piece together into pieces of a circle which is perpendicular to the boundary circle, exactly hyperbolic lines. In fact, this is a tessellation of the hyperbolic plane by fish, much like we can tessellate the Euclidean plane by squares, triangles, or hexagons. So, time to pause and reflect. We have seen that the history of geometry has other chapters that we never considered. Crafted by mathematicians who questioned the basics of Euclidean geometry over many centuries, even though most of them could not actually resolve their dilemmas with the parallel postulate. Geometry changed radically in response to their efforts, becoming a broader and a more complex discipline. But there is a question that many of you have right now. And moving to our remote audience, I'm going to let my cousin Jonathan ask it. So this is my cousin Jonathan. He is a professional soccer coach, and I'm so proud of him because I could never do what he does. But he has this question, and he asks it with great love for me, regardless. And there's his question. He's really thinking this right now. Okay? So, all right. So what is this hyperbolic geometry good for? Must it have applications, or can we just enjoy the beautiful pictures and the intriguing mathematics? So the first application is for the physicists in the audience who are already thinking this. Hyperbolic geometry is the geometry of special relativity, the theory introduced by Einstein in the early 20th century, approximately 100 years after Gauss developed his theory of non-Euclidean geometry. And if I were the wing professor of physics, I would elaborate on this for the next 10 minutes. As this is not the case, I want to share with you a different application of hyperbolic geometry, which I will introduce through a slide of words which seem incongruent not only with the beginning of this lecture, but also with the entire field of geometry. Not what you were expecting. And poor Gauss in the corner also looks just a tiny bit confused. So these are words which we hear in newspaper articles, and we definitely don't associate with geometry, especially hyperbolic geometry, which seems so unlike anything in our everyday reality. So in my remaining 10 minutes, I want to talk about an interesting use of hyperbolic geometry as it relates to neural networks. So first, what exactly is a neural network? The simplest answer is that a neural network is a computer program designed to work like the neurons in your brain. And this level of understanding is sufficient for us. Today, I will talk about a neural network which is designed to output a classification or identification of data. Now, some of you can use your imagination to invent many scenarios in which your personal data might be classified by a program or algorithm to draw conclusions about you which you might not support or might not fairly label all participants. In mathematics and data science, this is sometimes called algorithmic bias. I do not want to touch any of these scenarios today with a 10-foot pole. So instead, we will imagine a neural network whose job it is to identify photographs of animals. Okay. Input a photo, out comes a classification like, this is a marmot. They're cute. Now, my computer doesn't actually have a slot for inserting the photo of the marmot. So as part of this classification process, I must describe a method for turning my adorable photo into some sort of numerical data which I can put into my neural network computer program. So this leads to the question of how we can best represent our non-numerical data for efficient classification by a neural network. Suppose I were to represent this photo by a pair of numbers. So in reality, I would probably need a more complex numerical description. That pair of numbers would describe a point on a coordinate system, like in the xy plane. That is, a point in space. So I can think of a larger set of numbers describing my photo as corresponding to a point in higher dimensional space. And if I hope that my program would classify my cute animal photos effectively, a reasonable expectation is that all the photos of marmots would correspond to points in space which are close together. So, by the way, some of you out there, if you know where this picture comes from, you know that it doesn't really come from data with marmots, so just let it go. Okay? So, for example, I might want all the marmot photos to correspond to points in space in this yellow region, and all the squirrel photos to correspond to points in space in this purple region, kind of near the marmots, because they're both cute, small, furry, brown mammals. And I might want all the prairie dog photos to correspond to points like over here in purple, again, close to the marmots and squirrels, but in their own separate clump. With an image like this, I would expect my neural network to conclude that a photo whose corresponding point in space was somewhere in the pink region was a photo of a squirrel. Okay. But the animal kingdom is much more complex than furry brown mammals. So my program needs to know how a large variety of animals, and maybe plants and insects as well, correspond to points in space. Historically, scientists have depicted the variety in the plant and animal kingdoms and the evolutionary relationships between species in a phylogenetic tree. So here is a particularly beautiful example created by Fairhope Graphics, and we can see a variety of plants and animals and some insects over here. The branching in the tree indicates a sense of evolutionary distance between the different species depicted. So how can we assign each species a point in space in a way that assigns similar species to nearby points? A natural first choice would be to simply use a coordinate system with two axes. Okay. So In this case, our elephant over here would correspond to going 10 units in the horizontal direction and 30 units in the vertical direction. And that certainly gives a pair of coordinates describing every point on this phylogenetic tree a point in space. However, we see an immediate problem. The elephant and the peony, right, which I think we would agree are very, very different species, right, are far in evolutionary distance because to connect them in the tree, I have to go all the way back to the beginning and then out this other branch. But they're very, very close in their Euclidean or coordinate distance. Okay? So I might expect my neural network to classify them as similar species, much like the points corresponding to marmots and squirrels are very close together in my other image. I can see that some of you are looking distressed. They're not the same, I understand that. Okay. So how would a mathematician study this problem? Right? Well, the first thing is you would probably agree that the branches and bark of this beautiful phylogenetic tree are mathematically unnecessary. Okay? So a mathematician would create a mathematical tree which uses vertices or dots to represent branching points and species on the phylogenetic tree and connecting these vertices or dots with edges. So a mathematical tree corresponding to this image would look something like this. And I literally drew this over the tree on my iPad and slid it over here. Okay. While I am focusing on the decidedly apolitical problem of classifying species of animals, the discussion of this problem applies to any type of hierarchical data which can be represented in a tree-like format. For example, the structure of an organization or government is a hierarchical data set. So when I look at this mathematical tree, the elephant and peony problem is that when I try to draw this tree abstractly, there are points which are far in evolutionary distance, meaning that to connect them in the tree, I have to follow the branches back towards the trunk, but they're close in space when I draw them on paper. So a simple solution seems to be to draw the tree differently. Because my initial depiction was an actual tree, right, with branches and leaves, my mathematical tree is too vertical. Right? Maybe if I spread the branches out more evenly, I could solve the elephant and the peony problem, meaning they would be far apart in space as well as in evolutionary distance. So let's try that. So I am going to try to draw a tree with its branches very spread out. So this is as far spread out as I could get them, and it's looking pretty good. And I'm going to keep going. And I'm starting to get a little nervous because I have some vertices over here that are getting close in space, but the evolutionary distance between them in the tree is growing. So I'm going to keep going. And things are getting worse because if I look at the same vertices over here, they're very far apart in evolutionary distance, but very close on the paper. And I keep going, and things are getting worse. Right? The outer vertices over here, I can find two of them over here that are getting farther in evolutionary distance, but are very close in Euclidean distance. Okay. So now we see that even when I draw the branches of my tree as equally spaced as possible with enough layers in the tree, there are always going to be vertices which are very close together, even though the evolutionary distance between them is growing larger and larger. This means that we cannot solve the elephant and the peony problem by spacing out our tree branches. There will always be points like the elephant and the peony, which are close together but far in the evolutionary sense. However, if we view this tree in the hyperbolic plane, where points close to the boundary are actually very, very far apart, then there is plenty of room to draw this tree in a way that makes the elephant and the peony far apart in hyperbolic distance, as well as in evolutionary distance. So this example that I have shown you today that fixes this problem by putting this tree in the hyperbolic plane where these points are actually very far apart. Right? This problem that I showed you today is hugely simplified. In reality, it is unreasonable to reduce a complex photograph, for instance, to a pair of numbers. But as there are higher dimensional Euclidean spaces, there are also higher dimensional hyperbolic spaces where an analogous argument would hold. As you can imagine, efficient data representation is an active area of research, both from the mathematical and computer science perspectives. In the last few years, there has been an explosion of papers and proposals for using higher dimensional hyperbolic spaces to effectively model hierarchical data sets. My geometry classes were fortunate to have one of these authors speak to our class over Zoom in the fall 2020 semester. So the story of geometry spans many ancient civilizations, contains problems which lasted longer than a millennium, takes a variety of unexpected twists and turns, several divergent roads emerge, and surprising applications develop over a century after a huge insight and progress push the field forward. Geometry is a dynamic and changing discipline, as is mathematics, full of interesting characters who push its boundaries and urge it in new directions. So who changes geometry today? Expanding theoretical results, introducing new geometric approaches to old and new problems, perhaps problems where geometry was not a standard tool, increasing the scope of its relevance outside of mathematics. Well, so many people. And here are a few of them. From Miriam Mirzakhani, the first female recipient of the Fields Medal in Mathematics, to Dorothea Rockburn, a modern artist whose mathematical background pervades her work, to Moon Duchin, who uses geometry to assess whether districting maps have been gerrymandered, to many other active mathematicians pushing the limits and applications of geometry within mathematics. I am proud to know these mathematicians. I hope that tonight I have convinced you that the story of geometry, like the story of mathematics, is still evolving. This story lies both in books and in the creativity of mathematicians and scholars from many disciplines who actively use mathematics in their work. To my students in the audience and those who are listening tonight, I look forward to seeing how you will push the boundaries of mathematics and find new applications of mathematical principles. I'll end with a quote from Sir Marcus du Sautoy, a British mathematician who has devoted much of his career to sharing mathematics with a broad audience through books, articles, and television programs. He wrote, "Mathematics has beauty and romance. It's not a boring place to be, the mathematical world. It's an extraordinary place. It's worth spending time there." Thank you for spending time there with me this evening. Thank you. So there are so many people who are part of my mathematical journey in the audience, on live stream, and here in spirit. I'll begin by thanking my parents for always encouraging me to explore mathematically, first through Cuisenaire rods and geoboards, and later through challenging problems and mathematical summer programs. They taught me to be a fearless problem solver, and that an incorrect solution can teach you as much as a correct one, and that any problem can be put on a coordinate system. Well, almost any. I want to say to my students that there are many people, friends, teachers, and colleagues who supported me along my path and did for me what I hope I can do for you. It takes a community. I would not be the scholar or the educator I am today without them. And now some fun pictures. I will always be grateful to David Pollack, who I met on the very first day of 9th grade, and who taught me that math was more fun when you worked on it with others. With grace, humor, love, and patience, David made me understand that the joy of mathematics was independent of whether you were the top student on the math team. He was, I wasn't, and is nurtured in your mathematical community. I will always be profoundly influenced by Professor Paul Sally, who modeled the combination of scholar, educator, and mathematical activist that I have always aspired to be. With his passion for outreach, he worried about access before access was a word in the academic lexicon. He taught me never to stop trying to bring the joy of mathematics to young people. I know that he is here with me in spirit today. I have always appreciated the constant support of my undergraduate advisor, Professor Richard Beals, who has been in my corner for the past 30 years, even when it became clear that I was never going to be an analyst. Even as an adult, it means a lot to have someone in your corner other than your parents who is proud of your accomplishments. I had 3 influential professors as an undergraduate, Professor Beals, Professor Walter Feit, and Professor Daniel Mostow, who filled me with the joy of learning mathematics and challenged me with very, very long and difficult final exams. I still reflect fondly on those classes and what I learned from them. My graduate advisor, Professor Benson Farb, opened up the world of geometric group theory and taught me about mathematics as well as its content. I did not experience until later in my mathematical career the powerful support and community that female mathematicians provide for each other. Melanie Tulia, Moon, Katie, Carol, Allie, Bryna, and others, I am grateful for your support and for an occasional pep talk when I need it. Mathematics has always been a social activity to me, with the exchange of ideas, correct, incorrect, exploratory, as the highlight of research. The geometric group theory community is large and welcoming, seen here at the 50th birthday conference for my advisor. I have thrived in this dynamic group where I have found incredible collaborators, most of whom are hidden somewhere in this photo. When I arrived at Bowdoin in 2002, coming from larger places, I was welcomed by 2 local seminars in my field, one in Boston and one in New York. Over the past 20 years, I have given many talks in these seminars, learned about new directions in my field, and formed exciting new collaborations. In particular, I am grateful to the support that I received over many years as a new PhD, as a new mother, and as a more established researcher from Gilbert Baumslag and Bob Gilman at the New York Group Theory Collective. I am grateful for the wonderful students I have taught in my years at Bowdoin College. You make me want to come to work each day and ensure that I am always excited to step into the classroom. You patiently indulge my admiration for the underappreciated distributive property and endure the week when you are not allowed to use division in Math 2020. I look forward to seeing where your journeys lead you. I am thrilled tonight to see a group of Brunswick High School students in the audience. While I have met many Maine students in outreach programs over the years, this group is especially dear to me. They started working with me in the 3rd grade math club, progressed through 5th grade math team, years of junior high math circle, and for some, an entire Algebra 2 course during COVID times. I am so proud of what you have accomplished, and I know that wherever your studies take you, you will always retain an enthusiasm for mathematics and confidence in your abilities. The final and most heartfelt thanks tonight go to my family, to my children, who at this age knew the term Dista Leader Group, which they used liberally in conversation without having a clue what it was, just that it was something that mommy cared about, and for their patience with yet another gigantic lasagna, which was supposed to last for the 4 days I was away at a conference until Daddy provided better food. They look like this now. I would not be where I am today, personally, mathematically, and professionally, without the unwavering support of my husband, Tom. I know. From our early mathematical adventures, through graduate work, postdocs in faraway places, and finally settling in Maine, we have always been a team. You were always willing to watch small children if there was an important conference, and always made me laugh by putting the baby in those hideous plaid polyester pants every single time I left for a conference. We have worked together on local outreach, building the Midcoast Math Circle, and enriching the wonderful community of students at Bowdoin College. You have always encouraged my dedication to my research career and my service to the American Mathematical Society. When I doubted whether I had the seniority to serve the profession in this way, you never wavered, but reminded me that my leadership is meaningful to many. You are my compass and my guide, my intellectual partner and my partner in crime, well, maybe some mild mathematical crime. I can't thank you enough for supporting and encouraging me every step of the way, and I can't wait for our next adventure. This is my team. They inspire me every day to be the best that I can be. And thank you to them and to all of you for sharing this very special night with me. So I'm happy to take some questions, and I ask that if you have a question, you come down to the microphone so that the people on the live stream can hear as well. Or no questions is fine too. Oh.
I have a question I've always wanted to ask you.
Yes.
Is it possible to build a geometry with a finite number of lines?
So, I don't know the answer to that question, but I know where to look. I'm looking at Tom. There are finite geometries that have a finite number of, there are finite geometries with a finite number of points. So in that kind of geometry, by lack of infiniteness, they're going to be finite. But I think you mean in a broader sense, and I think that's the sense in which you would you would have a finite number of parallels. Yes.
So we can picture the spherical plane because we're standing on top of one.
Yes.
And I tried to imagine, as you were talking about the hyperbolic plane, myself inside the circle. Is the universe a hyperbolic plane?
No. But there are many wonderful online visualization tools. Here's another way to think about how you would visualize what it looked if you were standing in the hyperbolic plane. It's a perspective I didn't bring in, but I'll give you the brief overview. If you were standing in the Euclidean plane, it's flat. Your line of sight would go straight out forever in all directions. And if you were on a sphere, your line of sight follows the surface of the sphere. Now, we don't sense this standing on the Earth because the Earth is so large. But if you were standing on a smaller sphere, right, your line of sight would go away from you around the sphere. So what's left? If you're in a hyperbolic geometry, your lines of sight come back up around you. And the best way that I can imagine this, what it would look like to stand in a hyperbolic plane, this is called curvature. The Euclidean plane is flat, the sphere is round. If you're standing at a point in the hyperbolic plane, it looks like a Pringles potato chip. Some of it curves away from you down like that, and some of it curves up. So it's very hard to imagine other than standing on a Pringles potato chip. But people have made wonderful visualizations of what it looks like in the hyperbolic plane, and you can Google some of them. And in fact, there's this wonderful hyperbolic video game called Hyperbolica, right? All of you students who are on Steam, you can get it on Steam. And it will show you what it's like to walk around in the hyperbolic plane. We had the developer of this game speak to our geometry classes over Zoom, and he talked about what this Pringles-like curvature does to you and how he had to make the figures change as they walked around in the hyperbolic plane. It was very cool. No.
Jen, so exciting to see you up there. I still remember fondly Hyde Park. I did not appreciate the connection between hyperbolic geometry and classification models that you were sharing. And you talked about the marmot. Is it a marmot or is it a squirrel? 10 years ago, the data science couldn't make those distinctions. Now it can make very specific distinctions, but it can't do it's imperfect still. So if you go through a grocery store and you're doing image recognition and you're trying to identify, is that a cereal box of Cocoa Puffs or is it a cereal box of Raisin Bran? That's where a lot of the work that I'm doing and participate in is trying to figure out what is the limiting factor to be able to make those kind of distinctions so we can go beyond marmots versus squirrels and go to very specific, identification.
I think that's probably a more complex question than I can answer right now. I will answer so I think what you're really asking me is, can this embedding of data in hyperbolic geometry improve the tools sufficiently? Because you could imagine all of the varieties of food in a grocery store as a hierarchical data set where first you have cereal and then the cereal branches off. So I think you're really asking me, can this approach to better representation of hierarchical data have immediate consequences in the identification of cereal, right? And the answer is that it's slow. The structure of neural networks was built to rely on on Euclidean geometry. And so a lot of the work that's being done on using hyperbolic geometry in neural networks requires people to reinvent some of the structure that was set up for Euclidean geometry to adapt to hyperbolic geometry. So a lot of the numerical data that you would use to represent a photograph comes from Euclidean information. And so if you're really going to switch to a hyperbolic model, you have to figure out how to have what's called your feature vector represent hyperbolic data. So that's why there's been this huge explosion in the last few years, because people are figuring out that this is a better way to represent hierarchical data, but the structure of the programs that's been used so far has been built for Euclidean data. So I think there's still a lot of exciting work to come on that. Thank you oh, is that a question?
Yeah.
Sure.
I guess this is more out of curiosity more than anything. But in terms of the definition of a parallel line in the hyperbolic plane, would you ever be able to consider a parallel plane to the hyperbolic plane, maybe using the Euclidean plane in that case?
So if you want to talk about parallel planes, you have to go to a higher dimensional model of hyperbolic space. And that's way too complicated to get into tonight. But you could ask that question in a higher dimension.
Great talk.
Thank you.
My experience teaching mathematics for many years is that some students are algebraic and some are geometric. And I just wondered, you've done a lot of K-12 work. Do you see distinctions like that? I mean, one of the messages in your talk is how one can inform the other. But do you, this is left brain, right brain things. Have you seen, is that my imagination, or is it really true that some people have an algebraic, symbolic, or better at manipulating symbols and so on versus shapes?
I honestly don't think I've taught enough K-12 students because most of the work that I've done with them has been on topics that are way outside the usual curriculum. And so it's hard for me to assess whether when we're analyzing mathematical games or we're talking about king chickens on graphs, are we using algebra or geometry or both? So I can't really answer that because I haven't taught enough standard curriculum at that stage. But I definitely feel that on the college level, there are people who gravitate more to, say, analysis and calculus versus gravitating towards abstract algebra, for example. I mean, myself included. So, Karen.
Jen, lovely talk. Thank you. And thank you for the plaid pants reference. I know you purposely did not go into any detail on your research, but I would love to hear like the elevator speech version of how you use any of this in what you do in your research.
Mm-hmm. So if I go all the way back to the beginning, which I think I can do. Goodbye, pants. I don't know if there's a faster way to do this. I apologize. This is my whole talk in reverse. Everything disappears. If I go back to the very beginning here, right? So when you take something very abstract like this and you turn it into a graph in a very particular way, so maybe this is a better example for me to look at. This is called the Heisenberg group, right? So now this is three-dimensional. And so once I have something that's three-dimensional, I can say, well, look at this plane. So can you imagine that this plane continues right here? So I can look at that plane, and I can say, does that plane have spherical geometry, or Euclidean geometry, or hyperbolic geometry? And sometimes what happens is that because the way you make these geometric models is completely canonical, you follow a process, and so you then look for three-dimensional structures within there, and you can ask what the geometry is. And that geometry, for example, can tell you things about, so Karen asked the question, so I'm going to use a few advanced words, can tell you things about subgroup structure, for example, and for my students in my class, and tell you things about cyclic subgroups. So you take your thing, your group, which starts out looking very much like this, and you turn it into this picture. And once you have a way of measuring things, you have a way of talking about geometry. And then you want to know which geometry are you talking about. And then you want to tie the features of that geometry into the features of the algebra. So for example, I do a lot of work with a particular structure that's a little bit more complicated than this, which turns out to be, in its metric form, an infinite collection of hyperbolic planes, all of which are joined together on some line. And so you have all of this beautiful geometric structure that interacts with each other, and the goal is to take that and interpret it in terms of the algebra so that you can try to see what you're looking for, right? Nobody sees anything over here, right? And so the goal is to visualize it in some way and use the geometry to inform the algebra. So I'm not giving you any specific groups, but that is the general way that I interact with things. All right, well, thank you so much for being here tonight.